Maybe we should stop. All right, welcome everybody. Today we're very happy to welcome Jordan Wilson-Gerow from Caltech. Please take it away, Jordan.
Thank you. Thank you for the invitation. I'm going to talk about some work that was recently appeared in the archive, although the first time I gave this talk, that was in 2003. It just took a little while for this to actually come out. This is the letter, the long paper. This last one's an X, but hopefully it's this year. And I'm a little bit more optimistic in the two that I'm doing myself that I'll actually get them out this year. But I'll get to the exact content. But it's all based around this idea that we have a new kind of effective field theory-based approach for systems with extreme mass ratios. It was developed with binary black holes in mind, but I'll give some electromagnetism examples, and this really should be more general. And we definitely haven't exhausted all possible field theory models for which one could apply these ideas. Let me just get right into it. Right off the bat, Justin, I'm sorry I stole this from your paper. I drew it myself. I didn't cite you on this slide, but this is the basic idea. We're interested in binary black holes, and there are different regimes one could study. Of course, if you want to study big black holes that are nearby each other, if you're in a strong field, you need to do simulations, and that's hard to do. It's costly. This is how we do it for. This is how people do it to study gravitational waves for LIGO, etc. But that's hard to do, and you want to supplement that with other approaches, other approximation schemes, things to help you cover the parameter space more effectively. And so other approaches, another very powerful one is gravitational self-force. What is that? That is, I keep my big black hole in there. I use, say, the short-shot metric, but then I treat the other black hole as a perturbation. So it has a much smaller mass. It affects the spacetime more weakly than the original. And then I study corrections to that background spacetime, roughly speaking, induced by the gravitational field or the metric disturbances of that smaller body. Other approaches, and the ones that will kind of be the main point of this talk, involve treating both black holes as perturbations to a background spacetime. So in these upper approaches, you're in flat spacetime, you have some sources, and you treat gravity perturbatively, like you would literally draw in Feynman diagrams. This post-Minkowskian approach, I feel like half of this room wrote all of the papers on it, but that would be doing a disservice to some of our friends in Europe, etc. But really, this has just absolutely been pushed forward by people in this room. Some of my collaborators, Cliff, Ira, and Mikhail here, wrote a paper that really brought in the rest of the amplitudes community to start working on this. Me and all the collaborators showed that these amplitudes techniques in modern quantum field theory really can push the frontier on this. And ever since, it's been amazing what has happened when field theorists have entered the gravity regime. Now, what is post-Minkowskian versus post-Newtonian? They're both weak field. Post-Minkowskian, you're not expanding with g of order v squared. So you're not considering a virialized system, maybe a quasi-circular orbit. You're really interested in high eccentricities or hyperbolic scattering events. And why is that necessarily interesting? Well, from this plot that I stole from Justin's paper, when you have fairly highly eccentric orbits and you're out of the virial regime, even if you're bound, so E is less than 1, it might be that the PM is just the better, more approximate description because it retains all orders of velocity. Now, how do we tackle that regime? So there's been plenty of tools over the years to tackle the post-Newtonian regime, lots of classic tools, and also modern effective field theory tools like NRGR, non-relativistic general relativity. But for the PM, post-Minkowskian approach, scattering amplitudes or scattering amplitude-like objects turn out to be extremely useful. And why is that? It's because collider physicists and quantum field theorists in general like to keep Lorentz invariance manifest in their calculations and explicit, don't like to break it and go to a frame and assume small velocities, more or less for most situations. And so there are tons of tools coming from amplitudes for actually keeping all orders of velocity and talking about relativistic scattering problems. As I said, this would most naturally be described for scattering encounters, but it's also useful for eccentric orbits for the reason I had mentioned on the previous slide. And it turns out that there's actually just a beautiful way to analytically continue certain information from these unbound scattering orbits to describe the physics of bound orbits. It's actually remarkable that this is true. Finally, when do we expect highly eccentric orbits? Now, I'm not necessarily an astrophysicist, but I think it is fair to say that you expect it more for larger mass ratios. And the intuition is actually quite simple. If I have two big, heavy black holes, comparable mass, and they're orbiting each other, they're going to be radiating away their angular momentum much more efficiently than a system where I have a large black hole and a smaller binary around it. If you just look at the quadrupole moment, it's clear that that's true. And so for comparable mass black holes, you expect, at least at late times, to have more of a quasi-circular orbit. Whereas in this gravitational self-force type scenario, you expect more highly eccentric orbits. At least you expect to be able to see more, they'll be more abundant. And so taking these ideas together, it suggests that if you're interested in post-Minkowskian scattering, maybe you should focus on a self-force-like expansion, so large mass ratios. And this is exactly what I'll focus on. This is what we developed. It's a classical heavy particle effective field theory tailored for this. And right, we did this. I'm going to jump ahead for a moment. We did this using just point particle effective field theory. We didn't use quantum fields. We just literally wrote down like a Fokker action, like world lines, relativistic world lines interacting by exchanging gravitons. There is a field theory analog developed by Mikhail and Beatrice around the same time. And I believe that everything I will say here should apply to their approach as well. It's just really analogous. So jumping to the punchline, and then I'll get into some details. What we actually developed was a heavy particle effective field theory, which lets you use background field method, so Q of T in curved spacetime, and actually add systematic corrections to background field theory. Now, why do you have to add corrections? Well, obviously, if I just have a Schwarzschild black hole sitting there and I do scattering on it, I'm missing the fact that that heavy body can actually move. This is one place where you need corrections. And so we've developed a systematic way of understanding what that back reaction has to be. Then what we do is we write down some exact curved spacetime expressions. So it's true. Yes, we expand exact curved spacetime expressions for turbulent G. And this is a lot of the power that we'll have. Rather than building up Feynman diagrams and developing curved spacetime information order by order about flat spacetime, we're going to start from a curved spacetime description and unpack that in terms of its perturbative building blocks. And I'll show you what that means momentarily. Morally, what we're doing is perturbative self-force, the kind of thing I suggested should be done. It's not exactly that, but morally it's very similar. Using this, okay, what have we done? We checked the number of examples that had already previously been calculated. So, of course, through two loops, this was done in G and Company's original paper on the topic. Just Schwarzschild black hole scattering, understanding those dynamics. We computed that, checked it, it's all good. Just electric charges in Maxwell theory through two loops, computed that, matches, again, Sweet's group. I'm going to stop saying that. It's just the people in this room. I'll just say the words, the people in this room. Matches you guys' calculations. We also added some twists. So I'll point out why it was actually very easy for us to incorporate dyons in this framework, whereas if you're doing things in predictive quantum field theory, it's a little bit more subtle. Some other examples, putting some scalar or electric charge on one of the black holes in the other background. This is something that self-force people are very interested in. It's a Toei model for understanding how the self-energy in some field localized around the small body can modify its dynamics as it orbits. We computed that. The electric one was new as far as we understood, but the scalar one agreed to calculations for people in this room. And then I went off and took this further and did Rice-Nordstrom black holes and a bunch of black holes in modified gravity theories. There are effective field theory reasons why one would expect that these signatures should not show up in gravitational wave observables. But from a purely classical physics point of view, it's interesting to bound coefficients if we can bound them with logic. So let me get into it. Yeah. Just a word about what the cell force is. I don't think I need to go through all of this, but the idea is fundamentally is very simple. It's I have a stress tensor for my point particle, x dot x dot, I'm dropping all the indices, and it sources a background metric. So this is some Green's function. So it sources a metric. I want to get a Christoffel symbol from that, so I take a derivative. And now I have a background Christoffel symbol that I interact with myself. This is x dot Christoffel. And so it really is a self-energy, but it's in curved space-time. And this describes the correction to my motion for this heavy particle, or sorry, for this light particle in the background. Now, if this was just flat space, this propagator would be trivial, and we would normalize this away or use standard tricks. But this is a curved space propagator. And so what that means is it's actually going to change the metric, not just in a singular way at the location of the body, but in a significantly more non-trivial way that's actually going to affect the bulk motion of this body. In this cell force program, which is, it's really amazing that people do this, they aim to compute this exactly. And so it's a Green's function in curved spacetime, and I don't know of any analytic expression. I don't think it's known. And so they have to resort to impressive numerical techniques. They have to regularize things. It's tricky. Yeah, it's just a formal, or skip that. So what we want to do is take all the inspiration from them about just having a light body orbiting in some curved spacetime background. And we want to see if we can skirt some of those difficulties, especially the ones around regularization and gauge ambiguities, by doing perturbation theory instead of trying to evaluate things to all orders in G exactly. We want to take those ideas and apply them to perturbation theory, where we have ideas like dimensional regularization, normalization, vector field theory, things that where we can actually understand these divergences very systematically using DFT tools. And so this is our point particle effective field theory for that situation. So in cell force, they would have something analogous to this term, just a light point particle in a background. And we're going to model the heavy background as a point particle as well. This is how we're getting towards the post-Minkowskian approach rather than the true full-on cell force approach. So we just take these 2 point particles. I'm not talking about spin. I'm not talking about dissipative effects, tides, nothing, just the simplest possible model of the system, and couple them to Einstein gravity. And then I'm just going to expand the equations of motion describing the system. Really, I'm expanding the action about the limit that one of the masses is very small. And I literally, this is the derivation. It's a very simple idea. You take the exact solutions in that limit. So the heavy body is inertial. The metric is just the Schwarzschild metric. And the light body is a geodesic. All right, now it's just at the formal level. And you plug it in. And what you typically get, all of the first order variations, when you evaluate all the equations of motion, are supposed to cancel, but have neglected the stress energy of the light body. And so this term doesn't cancel. And so if I expand my action out, okay, this is the 0th order term, I have something like this, which says that my light body is actually sourcing gravitons in this background, and you have to account for that. Now, if you want to set up an EFT, you need a power counting, and our power counting will be in this ratio, M light over M heavy. And if you just work this out, it'll power count like M light squared. Why is that? There's an explicit M light in front of the light particle's action, and all of these deltas explicitly power count like M light because we're expanding about the probe limit. So what that means is I'm not done. I have to expand out delta XH and delta G to quadratic order in order to make sure I have all of the terms at order ML squared. And that's it to first cell force or 1SF order, meaning the leading correction to just probe background physics. But if I do that, I mean, this is actually a very simple theory. I have a linear source coming from my light particle's geodesic motion, and then I have a bunch of terms that are quadratic in delta XH and delta G. So in principle, I should be able to just do this and do the Feynman path integral, or say it another way, just solve the equations of motion, invert the wave operator. We will use that fact to make some nice simplifying formal manipulations, but at the end of the day, we won't actually be able to do that because we don't have an expression for that graviton Green's function in curved spacetime. It's the same problem that cell force people have. But the fact that we only need these quadratic orders will greatly simplify how we organize our perturbation theory. Importantly, so the issues I just raised were for the metric perturbation, but for the heavy particle perturbation, we can immediately just integrate it out. It's very simple. Why is that? Any non-trivialities in this action, when you expand about it, come in the form of the metric sourced by the heavy particle, evaluated at the location of the heavy particle. That's all you can get. You expand it out, you see a bunch of terms, but they all depend on this, or curvature is built out of this, localized at that point. Now, if you're trying to do things exactly, like not in a perturbation scheme, this presents it's a genuine challenge. How do you normalize this? How do you regularize this? But fundamentally, we're doing things to arbitrary order in G Newton, but arbitrary finite order in G, which means this metric is secretly built out of Feynman diagrams. It's some network of Feynman diagrams that says, I'm going to correct flat space to some finite order in G Newton. These are just words, but the technical statement is that the metric is locally flat in dimensional regularization. Now, this is a statement you can make in Feynman diagrams. You just do dim reg and you can see that all of these insertions always integrate to zero. But there's actually a really simple thing to do. Look at the d-dimensional Schwarzschild metric and take d minus 4 sufficiently negative. That metric is locally flat as r goes to zero. Very simple. And so what that means is that while this is in curved spacetime, when you do this expansion, the quadratic term that you get for this delta xh is literally a flat spacetime kinetic term. And we can just integrate it out. It's just free particle in flat spacetime. That same reason underlies why we can actually say that the solution to equation motion is inertial. It's inertial because we've renormalized away all of the divergent curvature at the location of the heavy particle. And so this is it. This is the action at leading order 1SF. I have my stress tensor of my light body. I have gravitons propagating in that Schwarzschild background. And then I have this new thing, which is what I get from integrating out the heavy particle. We call it the recoil operator. You can see it's non-local in time because a free particle has no restoring force. That's basically what that is. And so it's not like usually if you integrate out some heavy mode, this is gapless. And so corrections to it aren't suppressed by powers of that mass. Corrections to it are actually suppressed by that number and light, or that ratio. But we've been careful, we've checked to make sure that that is a sensible thing to do. It's just that we have a funny non-local operator in our effective field theory. These terms here, what are they? U is the background, is the forward velocity of the heavy body, and delta gamma is literally the difference in connection from the exact connection with the light particle and heavy particle sourced in the spacetime. It's the difference between that connection and the connection of the spacetime just sourced by the heavy particle. And this is it. This is all you need. And delta gamma is linear in delta G. And so you just have some simple theory of gravitons. It's quadratic. Like I said, in principle, you could just solve it. And to make things simple, I've drawn little cartoon pictures. So what is that order? Like I said, I have this source. I have this recoil operator encoding the effects of having that background there. And these graviton lines. And these graviton lines are propagating in curved spacetime. At 2SF order, I'm not going to write the formulas, but it's actually quite intuitive what you get. At this order, you get interactions between your fluctuations. You have now a kind of consecutive recoil, which is not exactly gluing two of these together, but it's quite similar to gluing two of these together. And then you also get recoil of the light body. And if you just work out the calculation carefully, it's quite literally geodesic deviation. So I have a light body that was on a geodesic. It gets kicked by one of these fluctuation gravitons, propagates, and then comes back. And if you look at it, it is geodesic deviation. And you can keep on going and developing more and more. But it turns out that for, but at least what is present day state of the art in PM scattering, you only need this part. So, okay, that was the story. Now let me talk about what we actually compute. Why is this useful? And so I said that post-Minkowski scattering, there's a relationship with scattering amplitudes. How is this related to classical gravity? This was explained by people in this room, that if one computes a scattering amplitude for this 2 to 2 process, there's actually a very simple relationship with a classical physics object called the radial action. You're not familiar with the radial action, it's quite literally the on-shell action or this scattering trajectory, but instead of holding the positions of your particle fixed, you hold their momenta fixed asymptotically. Simple observables like, say, the scattering angle immediately follow from radial action. It's like a generating function for observables for scattering trajectories. You can get other things out of it, or you can just have interest in the radial action itself. You can infer certain things that you might want to know about your system just from the radial action. And while scattering amplitudes naturally compute M, and there's a little bit of work to be done, but I think this group probably understands how to massage I out of it. What we can do with our point particle action is just compute I. We have an action for point particles, and we can just compute that on-shell action. Just plug in the solutions to the equation of motion. And so that's what we do. And it turns out that, I hinted at this on the last slide, that you don't need to do that much work in this mass ratio, this cell force expansion, to compute the radial action in perturbation theory. And that's because of these nice relationships that you get between these functions. So let me unpack this. So the radial action, I'm just stripping out some prefactors. At tree level, you have one function, okay. At one loop level, you have presumably two independent functions. These i's are functions of, I didn't explain this. B and sigma are the impact parameter, and B is the impact parameter, and sigma is like the relativistic gamma factor, or you can think of it just the inner product of the two forward velocities, the energy, something along these lines. And these i's are simple functions of sigma. And this form just follows just from Lorentz invariance and dimensional analysis. There's nothing deep to it, but it's extremely useful. Now, okay, at one loop level where I just was, in principle, there's a function in front of the light mass and a function in front of the heavy mass and a function in front of the light mass. But I just assigned labels to these things. This is just point particles in flat space-time. I called one of them H, one of them L. So there's actually no reason for these two functions to be different from one another. In fact, they're not. And so what that means is, although presumably you would need one SF information, you only actually have to compute 0 SF information at one loop. And then you can immediately infer what that function is. In the absence of charges, it's the same function. With charges, there's a little bit of relabeling to do, but it's quite simple. At two loops, you would imagine that you need 0 SF, 1 SF, and 2 SF. But again, that symmetry relation, labeling something light and heavy, and tells you that the two loop 2 SF contribution has to be equal to the two loop 0 SF contribution. A lot of words, but what it means is that all of this stuff that is 0 SF, so it's just probe motion, I can just get it from GD6 on this Schwarzschild background. This is a solved problem. And so to compute through two loops, all I actually have to do is compute this one function using my 1SF Feynman rules. And it should be clear just from the way the polynomials work out, the same is true at the next order GD. This is just talking about how you can reorganize it. It's fine. As I just said, 0 SF is just probe motion. And so I can just take my radial momentum, I just take my GD's equation, find my radial momentum, and integrate it along my curve to get the radial action. And like I said, this is a solved problem. I don't have the exact formula in my code, but I have, you can just code something up very quickly that generates any PM order you want extremely quickly. It's just a formula, literally a formula. So here it is to two loop order, but really it's trivial to get. The thing that matters is getting that 1 SF. Then that's where you have to do some work. So this is kind of heavy, so you don't have to look at it if you don't want to. But the point is very simple. What can I even draw? With very, very simple Feynman rules, I can only draw this, plus potentially higher recoil operator insertions. Turns out that those don't matter for what we need here. And so there's only two types of diagrams that you even need to compute this. They look like one loop diagrams, but because these are really curve space on gravitons, and this source isn't necessarily a straight line source, it's a geodesic, there's some extra unpacking to do. But all of that multi-loop information is encoded in these simple curve space Feynman rules. More concretely, what does one actually do? So this is the Light-Bordes stress tensor. It's a function, obviously, of the path of that geodesic that I'm calling X bar L. For scattering trajectories, I quite literally take a straight line, so impact parameter plus some inertial motion, plus corrections. For these curve spacetime propagators, I take a flat propagator plus a bunch of corrections. And all I have to do is take this exact integral, which I've written below, and just expand it to the desired order in G nu in terms of these variables here. There's no business involved in drawing all of the Feynman diagrams at a given order and figuring out what contributes. You just start from a single formula and you expand all of the things in the formula to the desired order. And all of this is known. I mean, D is the flat space graviton propagator, R is our operator that we've written down. Actually, I made a little mistake when I wrote this. These are just background field insertions on that flat space graviton propagator, describing that exact background that it's propagating in perturbatively. And this is just the geodesic. It's known, just expand it out. If you were to do this in Feynman diagrams, and Mikhail and Cliff did this, I think Cliff gave me this, there's a lot more work to be done. It's doable and you certainly get the answer, but by revisiting this same problem that's been studied since 2019, we're finding simpler and simpler ways to approach it. And of course, this is what you should do if you're trying to push the frontier. You should try to revisit everything and make sure you maximally simplify it. To SF, you have a couple more diagrams to draw. It's these three plus any insertions of that recall operator along these graviton lines. And that's basically the story. What is there to say? Yeah, this approach of writing curved spacetime Feynman rules has appeared in the literature before us. Galley and Hu had this idea, can't remember the exact date, sometime in the 2010s, of doing quite literally this, saying I have a point particle effective theory for my light body in a Schwarzschild background. Can I write down some Feynman rules that are curved spacetime Feynman rules to describe its motion? And they ended up landing on very similar diagrams to these. But there's a fundamental difference which makes this more practical, which is implicitly we always know that everything we're doing is to arbitrary but finite order in G nu, not to all orders in G nu. And this might seem like a strange technical point, but it's important. If you know that you're ultimately working in perturbations about flat spacetime and you have an effective field theory description, you have point particles describing your black holes, you know that you're actually working, you know exactly what you mean by your description. You know that it's an effective field theory. You know what your divergences mean. You know how to account for them. You know how to how to regularize them. We have useful tools from field theory to approach this. If you're doing everything as they suggested in actual curved spacetime, it's a much more difficult problem. And so this is why we think revisiting this offers some space for progress. So let me unpack a little bit about why this is useful. Again, you can ignore the formulas if you want, it doesn't really matter. But the idea is one can build, okay, this is the exact metric sourced by the heavy particle minus the flat part. One can build up all these corrections in perturbation theory. This is explained by Duff. The technical statement is if I have a heavy static source, I can compute the 1-point function of the metric in presence of that source. And of course, if I want to compute a 1-point function in the presence of a source, I have a bunch of Feynman diagrams to build. Imagine these flat, heavy black lines as just dots, like literally T nu insertions. And you have a bunch of graviton perturbation theory to build up, and you can get to an arbitrarily high loop, and you literally build up the Schwarzschild solution. And it's quite a cool fact that that's true. But what it means is that when you have things like this showing up in your perturbation theory, you don't have to actually compute them. You know that it's just equal to the Schwarzschild solution expanded to that order in G nu. So for example, these graphs, you can sum them, and the answer is a very simple tensor structure multiplied by what is effectively just log of Q squared. These are simple scalar integrals that people in this room can do immediately, whereas there's a little bit of work to be done to compute these, because these heavy black lines are legitimate graviton propagators. There's a lot of tensor indices, 4 graviton vertices. It's a mess. if you can simplify that into just a simple prefactor times log q squared or some other power of q, where q is the momentum exchange through the graph, clearly there's some simplification to that. A similar story happens for the motion of the light body. So I took two important ingredients from curved spacetime. I took the actual black hole itself. I said you can expand that out, and it's built out of flat spacetime Feynman rules. But the actual geodesic trajectory of that light particle in that curved spacetime is also built out of a bunch of perturbative insertions of gravitons affecting the motion of a point particle in flat spacetime. Again, you can unpack it. If you were to try and build this up from scratch, you'd have a bunch of ugly topologies here. And if you unpack our formulas, you can see that they have a very simple topology where, again, these heavy black lines were gravitons, and now they're scalars. It's all kind of iterative ladders. For those who care, this might be a simplification. For those who don't care, don't worry about this slide at all. It's a technical point that might help us push the frontier on integrals, but we don't know yet. I haven't actually carefully looked at that. But this is the basic idea. We take exact curved space-time information and we unpack it into its perturbative building blocks. And we know how to do that for all of the functions that appear in our EFD. Okay, computations and checks. So this is just scalar QED. I just fix some charge to mass ratios for the heavy and light body. And then I expand, assuming one has a much larger mass than the other. I can do everything I just said for gravity. And there's a huge simplification, which is obviously photons don't self-interact, and minimal coupling. And so my curved space-time Feynman rules are flat space-time Feynman rules. And all I have to worry about is insertion of this recoil operator and these simple point particle currents. And so you can again write down effective action, you have the source, you have your photons, you have your recoil operator, and you can just write down the exact all orders and coupling expression for the radial action here. And so this expression, not too much to unpack here. The only non-trivial things in this expression are these X bar lights, these trajectories of the charge orbiting the atom. There's no difficult curved space-time propagator to unpack. There's none of that funny business. That's why it's a very simplified model. The tensor structure is literally a bunch of constants, just arrangements of the Minkowski metric. And so in principle, just by expanding out these trajectories, one can generate arbitrarily high loop order at this self-force order for this simple model. It's not a very good model. It's not at all a good model as a proxy for gravity because it misses the field nonlinearities. But at least it gives you a handle on the kinds of integrals that might show up in your problem in a physical setup. Also, having a formula like this that is in all orders and coupling offers the possibility of numerical integration or something that isn't just expand in diagrams and evaluate complicated integrals. But again, we have to push that. Either we're excited at the idea. Super heavy slide. If you don't care, don't look. But this is just showing what I just said in words, how it can be pushed to for loops. People in this room already beat us to for loops, but just showing how simple it is, at least in QED. I take that expression, I have these currents, and I just expand them out in terms of the trajectories as this kind of form here. Right. The trajectories I can just literally work out. I know how to, I know what the trajectories of two charged particles orbiting each other are, or at least one static, one orbiting it. I can just solve it and expand it out. And it's kind of messy, but again, it fits on the page. I literally just plug in x1, x2, and x3 into this formula above, and I have the for loop integrand. Well, I have all integrands through for loops. Gravity is not quite so simple because of the complications of having that propagator and curved spacetime, but it shows a conceptual simplification that this describes a huge sum of Feynman diagrams. Right. You haven't been the handful of people in this room who computed this before. This is just a result, and it won't mean anything to you. But we actually took this and didn't just claim it works. We did get two loop integrals, and it works. This is the right answer. Also, yes, I hinted at diodes. So let me go back. This is kind of cool. the recoil operator, if you look at it, it's gauge invariant. It depends only on the field strength. These sources, okay, they're sourced by the light geodesic. If you look at the equation of motion for the light body, it only depends on FV. And so what that means is that both at this vertex, when you change a photon, and at this vertex, you'll only ever have contractions with field strengths. You never have a width contraction with two gauge potentials in it. And so there's no ambiguity in having a photon and dual photon present at the same time. And so you can actually lift this and give these charged particles both electric and magnetic charge without any ambiguity, because we know classical physics. And you can get the result for dyons also through two loops with not much more effort. You just have to notice this trick. At one loop, it's unchanged because everything's cosines, but at two loops, you start to see some changes. This is new as far as I understand. Now for gravity, let's unpack this. Again, totally same diagrams probably here in Miguel's paper. Want to give credit where credit's due. But what you have here is, again, two very simple curve space-time diagrams, and I'm going to extend it out to two-loop order, to order G cubed. At order G squared, you literally just have this, where T0 means just the 0th order stress tensor for that curved particle. So it's sort of for that particle in curve space-time. 0th order is just a straight line trajectory. And so this is almost trivial to evaluate. Here, I have the same straight line inertial motion stress tensors for my light body. And this one means I have a background field insertion. So I'm not literally in flat spacetime. I'm in curved spacetime and treating it perturbatively. And this is a linearized metric insertion of that background. At the next order, you have to insert a few more things. Sometimes you have a recoil operator, sometimes you have a background field insertion. I put this consecutive recoil operator in there because I just stole this graphic from a paper, but I already told you that at least in the region we're considering disorder conservative physics, you can just neglect that. On this side, you might have a couple background field insertions. You might have two indicating a higher order background insertion. So this is where the power of using the exact metric and expanding it out in terms of simple functions rather than building up into perturbation theory. This is where that power really shows. This is a very simple insertion into my Feynman diagram. I don't have to sum all those multi-graviton Feynman diagrams. And then this, same thing. I have background insertion, and then I might have to consider a correction to my trajectory, and I call that T1. But I already showed you all the trajectories for QED, that they're more or less just as easy to get for gravity. It's just something you plug and play with. And so you go ahead and you do the integration. I learned everything I know about two-loop integration from Miguel's paper. It's the answer. To unpack this in terms of Feynman diagrams, I'm not going to sum all of the crossings that one needs, but just like morally, the structure is this. The recoil operator is just, I follow graviton up, I'm here on the other body for a moment, I come back down. Same thing, but then on the way back, this graviton hits a background field insertion. And it goes on and on and on. But again, like I said, I didn't have to evaluate this contribution or the four graviton contribution. I just take the functions, plug them into my integrals. 2SF, similar story. Here, all of the sources, at least at two-loop order, are the trivial sources. It's a straight line motion, which means that these integrals become very simple to do. It's just a technical fact that it's just true. And you can just do these integrals actually pretty immediately. You don't need the fancy technology like differential equations and stuff. You can literally just do the integrals and you get the result. And a very important check. I talked about at the beginning about the symmetry between the heavy light, what you call the heavy particle and what you call the light particle, and that enforces a bunch of relationships between the radial actions at different orders. And so, we didn't think we did anything wrong, but we wouldn't have believed this whole story unless we computed this 2SF order at two loops and saw that it matched the probe contribution at two loops. That's when we knew that we were actually doing something correct. The one loop check also holds for sure. It was just a lot more trivial. It didn't require delicate cancellations. This was certainly not a trivial check. Good. So that's the idea, and those are the checks. And then, as I advertised at the start, I went and did a whole bunch of other fun stuff with it because it really was so simple. Of course, simple because I'm standing on the shoulders of giants, but we've really distilled out what needs to be done at this order. So, okay, if I want to add extra fields, I'm always going to have a recoil operator of this form. For different theories, this recoil operator, or this force, it quite literally is a force, might have a different form. So we're gonna have the gravity bit, and then if I'm in Einstein-Maxwell theory, I also couple to the field strength. If I'm in Dilaton-Gauss-Bonnet theory, I have some coupling to my dilaton field. What else had I considered? I already mentioned corrections in gravity don't change my recoil operator. This changes just my graviton. That changes the metric that I live in, basically. Dynamical turn Simons. Spherically symmetric solutions are charged under this, and so there isn't actually any modification to my recoil operator or to my sources, but it will modify this propagator here. It's kind of a simple addition, but something you can do. And then also the scalar and vector charge, these are the toy models for self-force. And so basically took all of these things and cranked it through using the ideas that I just discussed. For the more exotic models, I actually had to build up black hole solutions, but that's very simple to do because I'm not building them up perturbatively by summing Feynman diagrams with a bunch of new and complicated Feynman rules. I just do the same thing that you would do if you want to find the Schwarzschild solution given in your fourth year GR class. You onside a certain spherical symmetry, you get a radial ODE, and you just solve it. In principle, that might be difficult, but if you're interested in knowing the metric up to some finite order in G Newton, this is just a couple lines of Mathematica. It'll just spit out the metric to whatever order you want. And so, yeah, of course, if I have vector charge on both, this is just the Weissner-Nordström solution, I can just look it up. But for these other models, it's quite simple to just build up the black hole solution and to consequently to find the geodesic trajectories. Again, you're just doing more or less undergraduate GR and then extracting the information you want along the lines of the things I said earlier. Okay, this is just awful. What is the answer for the 1SF contributions for Weissner-Nordström scattering? I won't linger. And this is just proof that I did my homework for all those other models, the 1SF contributions. So let me go back because that slide is just hard to look at. Just kind of proof that we did it. What is there to say about this result? Of course, it's just some formulas, but how is it useful? Well, the vector charge, so Weissner-Nordström scattering, I found that just interesting. I just wanted to know what happens when you scatter Weissner-Nordström. It was investigated. I think Callum and Mikhail looked at it at 2 p.m. and for n-body scattering. And so there's already been work done in this, and I just wanted to see, can we keep pushing this since it's easy for us to build the integrams now? I also wanted to see, is there anything cool that happens if they're both extremal or if there are any games to play with all these parameters? Because I did have more parameters and I couldn't find anything interesting. There was nothing really to say for extremal black holes. We know for maximally supersymmetric black holes at one loop, there's a nice cancellation that occurs. And the two loops, you don't see the cancellation, but it doesn't affect the physics people were interested in. For n equals 2 supergravity, no such cancellation. Could have anticipated this ahead of time, but I check. So there wasn't anything interesting to see. There was a cool verification, I guess, of the result for Weissner-Nordström scattering. So there's all these parameters. You can take all kinds of limits. You can turn off the charge, matches Schwarzschild scattering. You can hold the charge fixed and take G Newton to 0, matched electrodynamic scattering. Take one of the charges to 0, and it matches the toy self-force models. All kinds of cool tricks. And something that you guys have already done in your Einstein-Maxwell paper that I also did here was say, let me take 2 extremal black holes and study their scattering in the slow motion. And why is that interesting? It's because you know that for like charges, extremal black holes, there are actually just solutions where they're just sitting there. And it's an exact solution on Einstein-Maxwell equations. So you can confirm that the radial action I compute vanishes as you take the static limit, and it does. And then the cool thing, which you guys also did, is you can actually compute the all orders in G d squared, so linear in velocity or leading in velocity correction to those solutions called the moduli space approximation. And people have worked out this metric on moduli space and lets you immediately calculate to whatever order you want, the scattering angle, whatever order in G-Newton you want. And I was also able to match onto that, give another check that I've done something correct. Finally, yeah, for these other models, I mentioned at the start. So especially over the last handful of years, there's been a lot of work talking about, what kind of higher dimension, what size can the coefficients of higher dimension operators in a gravitational theory, what size can those coefficients be while still being consistent with causality, unitarity, cherished principles? If we don't worry about that, and we really are saying, I don't care what those quantum physicists say, those quantum field theorists say, I'm a LIGO scientist and I just want to measure, I want to put a bound on that number, then what you want is an effective Hamiltonian or effective model which captures the dynamics of black holes as sourced by these things. My LIGO friends at Caltech genuinely care about these contributions and to see if they really do, to see if they can actually compute something like an effective one-body model, or to see what the gravitational wave signature of these extra operators would be. And so with these, it's not just formal fun and games to see how the extremal black holes work. Quite literally, you take this, you work out an effective Hamiltonian, and you give it to your LIGO friends, and you say, here, you can bound coefficients. I didn't work out any of the gravitational waveforms, but they can use this as input to their models, and they can do the waveforms. So they seem to actually care, which is quite exciting. So in summary, we put together a new effective field theory that is designed to study extreme mass ratios and is purely in the classical limit. Of course, there are other heavy mass effective field theories. Ours is different in that we're not actually talking about a field theory. The force carriers are fields, but the matter are literally particles. What this does is it uses the background field method and takes information from exact solutions rather than rebuilding it. At leading order, all you need is this recoil operator. And the next order, you only need basically two other operators. We checked it in tons of examples for 1 and 2 loops, and it seems to give the right answer everywhere we can check it. And for the new results, it passes all the consistency checks that we could throw at it. There are tons of new things to do. People in this room have used field theory methods to do most of these things already. So a lot of the results wouldn't be new, but adding finite size effects like spins, tides, absorption, something that might be novel with this formalism is a possible application of classical double copy. This is just words. I have no authentic thoughts about it yet, but very interested to see what we can do. This third point, I won't go into too much detail, but this one has the highest chance of actually turning this framework into something that can push the frontier. The difficulty is the same difficulty that gravitational self-force people face. They have some graviton Green's function in curved spacetime, and it's hard to evaluate. You have to use mode sums and eigenfunctions. Here, we can take that same idea, but because we're doing point particle effective theory, and we don't have a far zone and a near zone and some matching to do, we might be able to really push that. But this is, optimism, not concrete words. As I mentioned, in numerical integration, and then further doing this, radiation waveforms, all the things that people in this room have been doing using field theory methods and others. Lots to do, and hopefully this helps push a frontier. Hopefully it simplifies some things.
Yeah, so that was very clear. Thanks. This for-loop integrand, I guess that'll appear in your next paper. Or...
It wasn't going to, but I can put it in. It's just in my notebook.
Okay, but anyway, maybe we can you can show that to us so we can.
Yeah.
I mean, that one looks like something we could try to understand. Make some comparison.
For sure.
You check the near static limit in these different solutions that we found. And have you also checked the ultra relativistic limit to see if there's some universality in this
graviton dominance
model?
Yeah. Oh, I didn't look in the generalized models, but for Einstein Maxwell, I was expect graviton dominance. It just,
Yeah, but so for these new things, like where you have these higher dimensional operators, these should be then the dominant ones, right? Because
You would think so.
most of the movement on it. And then like you get direct access to this alpha coefficient in the high energy limit. So maybe
yeah, we can do it together. Which one has the biggest power sigma? I'm kind of joking, but it could be done.
oh, well, there's the numerator and the denominator, so that makes it's
Yeah.
abstract.
Yeah.
Yeah, no, I haven't looked, but I mean, the answer is here. I'm not good at doing math on the fly, so I'm not gonna try.
So all of these results you talked about are conservative?
Yes.
So, okay, so what happened to the dissipative part? And self-force? Typically, like, and you wrote down all of these expressions that are exact, or let's say, at a given order of mass ratio. Don't those include also the dissipative part? And so where?
Yeah, excellent question. So technical answer is I'm at two loops and I just restricted to the potential region. So I'm safe. I can unambiguously look at only my conservative parts. But for my all orders in G formula, the word exact, I need to be careful with that. When I say exact, I mean it's something that captures information at all orders in G, but doesn't capture all of the information at all orders in G. So for example, we'll never see horizon absorption effects in this, but any finite size effects we'll never see. But radiative dissipation, that is for sure still here. You just extend the integration over the full ultra-soft region and capture it. Of course, the same story holds for every other calculation. You can't just compute the radial action and expect to get your radiative observables. You have to compute something like an impulse. But there's nothing in what we've done here that really limits us to talk about the radial action. If you want to talk about a different observable, set up your in formalism and do the same game.
So in this scalar self-force model that you also mentioned, we computed at high enough loop orders to see this renormalization effects, right? That your EFT by itself, without including higher dimensional operators, becomes inconsistent because there's just some ultraviolet divergences that you cannot cancel. So how would that show up in your approach? You'd have to include somehow these higher dimension couplings of the heavy particle.
Yeah, that's exactly your mode. So yeah, I said all you need is the
before like if we had, I mean, we were quite confused for a little bit, and we like only late after the fact figured out that we need to include these higher dimensional operators. Do you see that?
Someone smarter than me might say yes, but I don't see it immediately. I mean, once you unpack into loop integrals,
in GR, at some point we need the dynamic love operators.
for sure. That's what I'm saying. This point particle EFT, those recall operators have all orders in G information, but it's not everything to all orders in G. And so at a given order, you're always going to have to supplement it with the appropriate high dimension operators. There's no way around that. That's why I mentioned numerical integration for QED, but for gravity.
But you're missing exactly all of these effects. So you're like, even numerically, like not including these effects, you would never be able to match like a numeric SF at high enough precision, right? Because
Absolutely.
Because you are exactly missing the horizon. And all of these things are exactly related to the horizon. That there is a horizon.
Yeah,
So
fundamentally.
but the place, of course, where that happened was as soon as he said point particle effective field, then he's in the same boat we are in.
No, I mean, at any given order, you can power count and know what you have to add. So, that's why I said we haven't solved self-force. We haven't said, here's how you describe the self-force problem to any order. No. But to use self-force ideas for PM, then I think there's some usefulness here, utility.
Yeah, so at some point, when you integrated out the heavy mass,
When I integrate that mass,
you arrived at this non-local term. And the non-locality can't really expand it out in inverse powers if they're heavy math. So can you explain again why that's not a problem?
Yeah, it's a super important question, actually. So typically, we do T, we want a local effective theory, and we get that because of that fact that there's some heavy mass scale, and so for all practical purposes at long distances, it is local. And it's that heavy mass scale that serves to suppress the higher operators. And so if you have a non-local operator, then the question is what suppresses further non-local operators? And the win here is that we always have every such non-local operator has a certain power counting with that mass ratio. We've carefully thought through this, and it turns out that at 1SF, this is the only operator that you can add that has the appropriate power counting. So all the other ones are more non-local. There's no way that we haven't landed on a nice, simple, local effective description, but we know that those higher non-localities will contribute at higher orders in self-force. And so it's really a statement that, how do I say it differently? It's more of a statement about coupling constants than it is about local effective field theory expansions.
So how does this your R3 or R2, whatever, like the second S2SF recall operator look like? Are these just two factors of 1 over d tau, and then 3 of these
Basic
gamma?
Yeah. But then it's just down by an L.
Any final questions? If not, let's thank Jordan again. Great. Okay.